Hello students. So here in this lecture we are going to learn one more bottom up approach, okay, which is called as precipitation and co-precipitation. Okay, so this is a technique by which you are able to prepare the nanomaterials, nanoparticles, particularly in thin film form. So let us try to understand how you are able to prepare the nanomaterials by using this precipitation method. What is precipitation? So precipitation is the process of compound coming out of solution. Okay, so as I said, basically this is a bottom up approach, and the environment is of course liquid phase synthesis technique is this, because the environment in which these nanoparticles are going to form is liquid. Okay, so you can imagine that we have here a solvent and a solute. Okay, so what is precipitation? Is the process of compound coming out of the solution. So in the solution you are forming a compound, and if that compound forms, then you can call it as a precipitation. It is the opposite of dissolution process. Okay, so basically dissolution is known to all of you. Okay, so what happens in dissolution? Where the solute particles separate from each other and are surrounded by solvent molecules. Okay, so this is the dissolution process. So if you put some solvent in the solute, then if you put some solute in the solvent, then you will realize that the solute slowly start to get dissolved in the solvent. So this situation is shown in the schematic image in the first stage of schematic image, where you can see that it is represented with the label A, and we call this as an unsaturated solution. Okay, so you can see in this image that there is a beaker which have a solvent, and we are going to add some solute. So solute is in the solid form. So when a solid solute is added to a solvent in which it is soluble, then solute particles leave the surface of the solid and become solvated by the solvent, initially forming an unsaturated solution. Okay, so here the rate of leaving the solute particles from the surface of solid is very high. Okay, so all the solute particles, basically they are leaving the surface of the solid and become solvated by the solvent. So this is the process of dissolution. This is the process of dissolution. Okay, in the second case, what you can see, okay, is B, that is a saturated solution, because basically that solute is getting dissolved in the solvent, okay, and it keep on dissolving. Okay, and we know that as the solute is dissolving in the solvent, the concentration of the solute in the solvent goes on increasing. So then concentration reaches to the saturated solution. Now what happens in the saturated solution is that when the maximum possible amount of solute has dissolved, the solution becomes saturated. Above that it is unless and until we are not supplying an additional energy in the form of heat or some kind of mechanical energy, it is not going to dissolve. Okay, so this means that what happens, it is not getting dissolved, means that the rate at which the solute particle leave the surface of the solid is equal to the rate at which they return to the surface of the solid. Okay, so in equal amount the particles of solute is leaving and again is returning to the surface of the solid, and because of that this situation, what happens, the system is the solution has reached to its saturated condition. Now what happens for supersaturated solution is shown in figure C. So in a supersaturated solution can usually be formed from a saturated solution by filtering off the excess solute or providing thermal energy. Either we can filter the saturated solution, or we can additionally provide some amount of energy so that it can further dissolve, and if that happens then you will realize that the solution goes to the supersaturated state. Okay, and in that case when the solution has reached its supersaturated state, in that case if we add some kind of a seed solution, okay, then what happens, if we add some sort of seed solution, then we can see that it started to precipitate. Okay, then we can see that it is started to precipitate. So that situation is shown in the image D, where when a seed crystal of the solute is added to supersaturated solution, then solute particles leave the solution, so opposite of dissolution. Okay, so here what happens, the solute particles leave the solution and forms a crystalline precipitate. Okay, and that is the reason we call that precipitate is opposite to the dissolution process. Okay, so you can see that the seed can be in the form of a crystal, or even some sort of other way you can supply. Suppose some kind of a thread, okay, is supplied, then it has been observed that there is a precipitate is take place. Okay, so as you can see that it is opposite of dissolution process, and where the solute particles separate from each other and are surrounded by the solvent molecules. So in precipitate what is happening, basically the solute particles find each other, okay, and form a solid together. So basically the solute particles find them each other and form a solid together. Okay, so this is called a precipitate, or sometimes it is abbreviated as PPT. So PPT is a short form of precipitation. Okay, so both are same. The precipitate, you can call it as a precipitate, or you can also call it as a PPT. Okay, so the rate of precipitation and dissolution process determine the overall effect. Okay, whether there is a material is forming or it is dissolving, it depends on what? It depends on what is the rate of precipitation and what is the rate of dissolution. If the rate of precipitation is higher than the rate of dissolution, then you can call it as a precipitation. If the rate of dissolution is higher than precipitation, then you can call it as a dissolution process. So what is a co-precipitation? Okay, so co-precipitation is used for simultaneous precipitation of more than one component. Okay, so here basically it is not a single component, we have to add one more component which will help to precipitate, to initiate the precipitation, and if this is the case, then we call this precipitation as co-precipitation. So precipitation is formed due to heterogeneous nucleation process. Okay, however co-precipitation is formed due to homogeneous nucleation process. Now here it is very important, okay, to to all of you to understand this, that let me remind that this for these nanoparticles are get formed by two important steps, as already I have discussed with all of you. Okay, so first step is nucleation and second step is growth. Okay, now in nucleation there are two types of this nucleation. Okay, so first type is called as an heterogeneous nucleation. Okay, and second type is called as an homogeneous nucleation. Okay, so in one case of nucleation, okay, you don't need a type of a seed crystal. Okay, in one case you need a seed crystal. If it don't need a seed crystal, then you can call it as a homogeneous nucleation. But if you need some kind of support, some kind of a seed crystal to for the nucleation process, then you can call this as a heterogeneous nucleation. Okay, so just keep this in mind, that there are two types of nucleation. Okay, if you want to imagine this, then you can keep in mind that in the sea, okay, you can see there are some ice lands are produced. Okay, big crystals of ice are produced in the sea. Okay, so what happens, how they get produced in the sea is an example of a homogeneous nucleation, because there is no some seed is required for the growth of ice in the ocean. Okay, in the sea. Okay, but there is another kind of nucleation is take place, which is called as an heterogeneous nucleation. Now you can also imagine this heterogeneous nucleation in where there is a production of these sugar cubes, sugar single crystals. Okay, sugar single crystals. So suppose if there is a supersaturated solution of sugar, okay, and if you just insert a thread inside that solution, then you will realize that the thread, it has started to grow the sugar in the form of crystals. Okay, so that is a example of heterogeneous nucleation. So that's why you have to keep in mind that for precipitation you need to insert a seed crystal, and because you insert a seed crystal, there is a further growth of that crystal, so that is a precipitation. But whereas in co-precipitation, basically you are not supplying a seed, you are supplying another solvent which initiate this precipitation process. Okay, so as an example, we are trying to learn how to make a material, okay, by using a co-precipitation method. Okay, because this is a very simple and effective method. So one of my student has carried out this reaction, and just I take this opportunity to share with all of you, so that you will you are able to imagine how you are able to make this nanomaterials by using co-precipitation method. So the steps are very simple. You just need some beaker, water, some chemicals, and the stirrer. Okay, so what is prepared in this slide is the material which is called as bismuth vanadium oxide. Okay, so BiVO4. So this is the chemical formula of that material. Okay, now basically as there are two metal elements are observed, one is bismuth and second is vanadium. So you need a precursor of bismuth and precursor of vanadium. So in the first case, the bismuth bismuth NiO3 is dissolved in the distilled water. Okay, and acetic acid, some sort of acidic solution is required for the dissolution of BiNO3 at room temperature. So you just dissolve it in 1 molar proportion in the water. Okay, double distilled water. Similarly, okay, NH4VO3 is another precursor where you can take it in a separate beaker and dissolve it in distilled water, but at this time you may need to supply some sort of heat energy like 75 degrees centigrade. Okay, so now you have two different beakers. Okay, you have one solution where you have dissolved BiNO3 in water, okay, and acetic acid, okay, that is shown in the first photograph of this on the left hand side, and plus we are going to we have also a solution where NH4VO3 is dissolved at 75 degree in the water. Now when we are going to add these two solution, what you can see is a BiVO4 precipitate take place. Okay, so initially the solutions were was very clear because there is no precipitation. Okay, but when you add these two solutions, then you will get a turbid solution where we call this we call that there is a co-precipitation has take place. Okay, and when you further wash it and dry it, okay, then you will get the material in the powder form. So when you are able to take the scanning electron microscopic image of this material, then you can see that image is shown here, where you can see that the scale bar which is given on this SEM image is 500 nanometer, and you can with the help of that scale bar you are able to find the on an average particle size of these materials, and you will realize that it is in the range of nanoscale, that is below 100 nanometer. So this is a beautiful example. A very simple technique is able to prepare this BiVO4 powder in the nanoscale. Okay, so that steps are again I have mentioned here. So in the first step, BiNO3 is dissolved in the distilled water and acetic acid at room temperature. Then in the second stage, NH4VO3 were separately dissolved in distilled water at 75 degrees centigrade. In the third step, both solutions are mixed, resulting in the formation of solid BiO4 precipitates. The precipitate was centrifuged, okay, washed with the distilled water several times and dried in oven at 60 degree for 6 hours. Now, BiVO4 nanoparticle powder was obtained after annealing in a conventional furnace at 600 degree centigrade for 1 hour. So this is for crystallization of this BiVO4 powder. Okay, so generally metal oxides like Al2O3, SiO2, zinc oxide, TiO2, zirconium oxide, all these kind of materials, okay, nanoparticles can be produced by this approach. So this is very useful approach. Okay, now let us try to understand that what are the parameters which basically is going to control in this co-precipitation method. Okay, so what is the effect of raw materials? Okay, so what is the starting raw material you have to take care for this kind of technique. So let us try to understand what is the effect of raw materials. So very generally, okay, or broadly, nitrates and acetate salts, okay, so let us say bismuth nitrate, okay, or any kind of zinc nitrate, okay, or any kind of zinc acetate. So such kind of salts are preferably used as a metal precursor. So most of the nitrates and acetates are preferably better to use as they easily dissolve in water. What is the intention behind it? Because they can easily dissolve in the water. But ammonia or sodium carbonate and ammonia or sodium carbonate, you can use it as a precipitating agent. So they are very common, ammonia, KOH, okay, or sodium carbonate, okay. So these are very common agents, okay, precipitating agents basically you can use for to make that precipitation happens. Okay, now chloride and sulfates ion act as an poisons. Okay, so these metal precursors are also available in the form of chloride and sulfates. Okay, but they are poisonous. They are poisonous in nature in many catalytic processes. so better to avoid. So they are poison, so it is better to handle non-poisonous precursors because they are not harmful to the environment and to human beings. So it is better to use the nitrates and acetates. However, if used, but even if we use the chloride and sulfate, even if they are poisonous, then they need repeating washing steps to remove these ions from the precipitate, because it is not easily they get removed from the salts. So you need to do multiple washing steps in order to remove this chloride and sulfate. Okay, so this is a one aspect as long as the raw materials are concerned. So we have seen that what is the effect of raw material. The second important parameter is pH of the solution. Okay, so let us try to understand what is the effect of pH on co-precipitation and its a final product. So pH is directly control the degree of supersaturation and hence is expected to affect the final properties. Okay, because as we have seen that basically this nucleation and growth process, this all is controlled by this concentration of the solute. So definitely the pH plays an important role while forming a material. So in some cases higher is the pH of the precipitate, lower the size of the precipitate product. So it has been observed by researchers that if you precipitate your if you precipitate the material when the pH of the solution is high, then what final product you are getting should have low particle size. Okay. In Al2O3 system, the precipitation pH determines the phase formation. So that is for another material, but particularly if you take some special material like Al2O3, then it has been observed that the pH also determines the crystal structure of the material. For example, the precipitation in alkaline medium forms birate, that is the beta phase of Al2O3, while the precipitation in more acidic condition forms bohemate, that is gamma phase of Al2O3. So just say material is same, Al2O3 the material is same, but it has different crystal structures, and depending upon the different crystal structure it has different phases like beta phase and gamma phase. Okay, so whether you want your material in beta phase, then you have to take care of that particular pH value. If you want it in gamma phase, then you can change the pH accordingly so that your final product will be in the gamma phase. So you can realize that the pH is basically able to control the size of the material as well as the phase formation of the final product of the material. The next point is very obvious, that is the concentration of the solution. Okay, and what happens to the if the concentration is low or concentration is high? It is very easy to understand that it is desirable to precipitate at high concentration levels of metals for faster precipitation. If the concentration is higher, the precipitation is faster. Okay, so if the concentration is high, precipitation is high, then what you get is the final product that is high. That's why this increases the yield by decreasing the vessel volume for same amount of precipitate. Okay, so if you are trying to get a more powder at the end of the reaction, then what you have to do is you have to increase the concentration of the that solution. Higher concentration of precipitate agent results in smaller particle size, okay, and high surface areas due to increased nucleation rate. Okay, so there is one more relation, that if you want the particle size lower, then what you have to take is you need to make a higher concentration of that precipitating agent. If the precipitating agent is more stronger, then it is able to make the material in with low particle size. Okay, is there any effect of solvent? Okay, what kind of solvent is preferred? That is what we can see. For preparation of bulk product, water is almost exclusively used as the solvent for economic reason. Okay, water, if you have your salts which are easily dissolvable in water, then this is fantastic, right? Because water is easily available to all of you, and it reduces the cost of the reaction. You can also use organic solvents, but they are very expensive. Hmm. You can also use organic solvents, but they are very expensive, and they are also environmentally hazardous. Okay, but water is cheap. It is not non-hazardous. Okay, you can just use it very normally. Okay, so so use of organic solvent is very limited to obtain better product quality. Okay, so there are certain advantages of using water as compared to the organic solvents. What is the effect of temperature? Now you can think that, okay, now you can think that the temperature can also affect the precipitation. Now in the last slide you have seen that one of the solution which we have prepared for vanadium case, you need to supply some sort of heat energy that is at least 75 degrees centigrade. So if you so in that case, okay, in such cases the temperature is useful to see how we can control the particle size. Okay, so nucleation and growth rates are extremely sensitive to temperature. Okay, so the nucleation process and growth process, both these processes are basically sensitive to temperature, whether you are doing your reaction at room temperature or if you are doing it at 50 degrees centigrade or 100 degrees centigrade. So all these matters on your final product. In general, most precipitation processes are carried out above room temperature for more rapid precipitate. Okay, so basically you can understand this, that if the nucleation and growth process get the rate of nucleation and rate of growth increases with temperature. Okay, so if the temperature is low, then the nucleation process is very slow, growth process is very slow. If temperature is higher, then the nucleation is a faster process, also the growth process is faster. Okay, that you have to keep in mind. Okay, so that's why what happens in most precipitate process are carried out above room temperature, because we don't want to give it enough time. We don't want to wait for longer time. If you want your product quickly, then you have to increase the temperature. The precipitation temperature controls precipitate properties. Okay, so temperature not only control the nucleation and growth, but it also control the precipitate properties such as the crystallite size, surface area, and the phase form. Okay, so all these factors are necessary. So whenever you want to make this, you want to prepare the nanomaterials by co-precipitation method, it is important to take a note of these parameters, because these are the parameters basically where the phase, composition, purity, particle size, surface area, pore size, all this is going to get these properties are going to depend on what is the temperature of the during the precipitation, what is pH, what is solvent you are using, what type of composition you are taking, what is concentration of the solute and solvent, what are the additives, what is the raw material. So all these factors you have to take care whenever you are preparing some nanomaterial. Okay, so most of the parameters we have already discussed. Okay, just in a summary, we have given this again in a pictorial form for just to keep in mind that what are the parameters and how they are going to affect. Now what is the advantage of this material? The main advantage of this process is a possibility of creating pure and homogeneous material. So it's a very simple, cost effective, okay, and you are able to make a pure and homogeneous material. What are the disadvantages? The major disadvantages include necessity of the product separation after precipitation. Okay, it is not like that whatever you are getting, okay, is the final product. Okay, like in PLD, in sputtering, okay, in chemical vapor deposition, in ALD, what you was looking that whatever you are getting the thin film, you did not to wash it again. Whatever you are getting is your final product, but here you have to separate it. and then generation of large volume of unreacted salt containing solution. So there are unreacted material and salt is remaining in the precipitate itself, so it is necessary to wash it very carefully. Second disadvantage is there is also difficulty in maintaining a constant product quality throughout the whole precipitation process if the precipitation is carried out discontinuously. Okay, so it is like I have to say that if you are not keeping the parameters which we have discussed, like temperature, pH, solvent composition, concentration, okay, if they are not constant for the next reaction, then something is going to change in your final product. Okay, so it is more sensitive to parameters. Okay, so if you take care of these parameters, then the quality of reproducibility is higher. If you are not taking care of enough accuracy of these parameters, then the final product may be slightly different. Okay, so this is what about the chemical co-precipitation technique, and we will see micro emulsion technique in our next lecture. So for right now we are going to stop here. Thank you.